Good morning and welcome to a new course about systems of ordinary differential equations. In this course, we'll finally see how to solve these systems of equations by using the matrix exponential. Okay. So the general problem that we'll be solving is a system with n equations and n unknown functions. All of the n equations are linear and have constant coefficients. So the coefficients are these numbers. So these are supposed to be numbers, A11, A12 up to A1n. And in the second equation, A21 up to A2n. And the last equation, AN1 up to ANN. And these equations also have source terms, which are functions of t, b1 of t, b2 of t up to bn of t. And these source terms could be zero, in which case the equations would be homogeneous, or non-zero, in which case we have to deal with the contribution of the source terms. In our case, the coefficients are constant. This makes the equations significantly easier to solve. If the coefficients are non-constant, so if the coefficients are functions of t as well, then there is no good general method. Certainly nothing like what I'm going to show you in this course. So it's important that the equations have constant coefficients. The matrix formed by these coefficients, which we call capital A, is the system matrix, also called the coefficient matrix. And it is a square matrix because we have n lines, so one line for each equation, and n columns, one column for the coefficient of each unknown function in each equation. So let capital Y of t be the column vector made of the unknown functions. So it is a vector with n components written as a column like this, y1 of t, y2 of t, up to yn of t. And let capital B of t be the column vector made of the source terms, b1 of t, b2 of t, up to bn of t. Then the system can be written in matrix form as y prime of t, or dy over dt, so the derivative of y with respect to t, is equal to the product between the matrix A and y plus the vector b. So it turns out that all this part of the system, so almost everything on each row, so from A11, Y1 to A1N, YN, whatever, and from AN1, Y1 to ANN, YN. So all of this is the product of the matrix A and the column vector Y. And then we have to add the source term, which is represented by the column vector B. It turns out that by writing the equation in matrix form, we obtain a very straightforward solution formula. Namely, if we look at the equation with no source term, so it's the homogeneous version of the equation where all the source terms are 0, then the equation y prime of t is equal to a y of t with the initial condition y of t0 is equal to y0 has a solution y of t is equal to the exponential of a times t minus t0 times y0. And if there's a source term as well, so if the equation is y prime is a y plus b with the initial condition y of t0 is equal to y0, then the solution is y of t is equal to e raised to the power a times t minus t0 y0 plus integral from t0 to t of the exponential of a times t minus s applied to b of s and then integrated as a function of s. So this is a vector valued function, and when we integrate it, we need to integrate each component separately. And the output is again a vector. So let's again notice the resemblance between this formula and the one we would use to solve a similar problem without matrices, just a first order linear equation. So if we look at the equation, y prime is equal to ay plus b with the initial condition y of t0 is equal to y0. So where these are now functions, but without any vectors, then the solution is y of t is equal to e raised to the power a times t minus t0 y0 plus integral from t0 to t of e to the a times t minus s b of s ds. So the formula looks almost exactly the same, except that it involves the exponential, the usual exponential, instead of the matrix exponential. So let's prove that this is the correct formula by solving the equation. Let's move ay to the other side, and we get the equation in standard form, y prime minus ay is equal to b. Then multiplying the equation by the integrating factor, we get that, so first, what is the integrating factor? It's e raised to the integral of the coefficient of y. So it's e raised to the power integral of minus a dt, so it's e raised to the power minus at. So we multiply both sides by the integrating factor, e to the minus at, and we get that on the left-hand side, we get e to the minus at y prime minus a e to the minus at y, which by the product rule is the derivative with respect to t of the product e to the minus at times y. And on the right-hand side, well, since we multiplied by e to the minus at, we get e to the minus at b of t. Okay, so now in order to use the initial condition, instead of taking the antiderivative, we take the integral over an interval. So let's integrate both sides from t0 to t. So on the right-hand side, we get integral from t0 to t of e to the minus as b of s ds. So I changed the name of the variable from t to s because now I'm using t as one of the integration bounds. And on the left-hand side, the integral of the derivative by the fundamental theorem of calculus is the difference between the function evaluated at t and the function evaluated at t0. So it's e to the minus at y of t minus e to the minus at0 y of t0. So then let's move e to the minus at0 y of t0 to the other side, and we get e to the minus at y of t is equal to e to the minus at0 y of t0, which is y0, plus integral from t0 to t e to the minus as b of s ds. So in order to get y of t, we multiply both sides by e to the at, which cancels e to the minus at on the left. So I get that y of t is equal to e to the at e to the minus at0 times y0 plus e to the at integral from t0 to t e to the minus as b of s ds. So e to the at times e to the minus at0 is e to the a times t minus t0. And same for the integral, we can put e to the at under the integral, and e to the at times e to the minus as is e to the a times t minus s. And this gives the formula that we wanted to prove. So pretty much the same proof should work in the matrix case if the matrix exponential has similar properties to the exponential of a real number, which is what we use here. So e to the minus at. So if the exponential of a matrix works in the same way, then the same proof would lead to the same formula. So for linear first order equations, however, when we use this method to solve them, we don't need the coefficient a to be constant. So a could be a function of time. And then we just use the method of the integrating factor. For matrices, a has to be a constant matrix. So this is why we need a system with constant coefficients. In general, for systems of linear equations with non-constant coefficients, this method does not work. So it may still work if the coefficient matrices commute, but we won't get into those issues. We'll just assume that the coefficients are constant. So what is the matrix exponential that we want to use and compute? The exponential of a matrix A is by definition given by the same power series, so the same infinite sum that can be used to define the exponential of a real number or of a complex number. So it's equal to the identity matrix plus a plus 1/2 a squared plus 1 over 3 factorial a cubed plus 1 over 4 factorial a to the 4th, etc. So it is the sum for n going from 0 to infinity of 1 over n factorial times a to the n. So it's a similar formula to the one that we would use for a real number or a complex number, except that for a real or a complex number, the first term would be 1 instead of the identity matrix. So the identity matrix is the matrix that has 1 on the main diagonal and 0 outside of the main diagonal. So it must be the matrix, the identity matrix with the same dimension as A. So for each size of a square matrix, there exists one identity matrix of that size. So there exists a 2x2 identity matrix, a 3x3 identity matrix, etc. And I here is the one that has the same dimension as A. And the exponential of e to the at is defined in the same manner. So it's identity plus t times a plus t squared over 2a squared plus t cubed over 3 factorial a cubed plus t to the fourth over 4 factorial times a to the fourth, etc. So it is the sum for n going from 0 to infinity of t to the n over n factorial times a to the n. What does it mean to have an infinite sum of matrices? We compute the sum for each entry. So all of these are matrices of the same size, and when computing the infinite sum, we add for each entry the contributions of each term in the infinite sum. So each entry of e to the power at, or of e to the a, is given by an infinite sum of the entries of the terms in this definition. And each of these sums converges. We're not going to prove this in this course, but the proof is not very hard. So this definition by an infinite sum is guaranteed to produce a valid result because it converges for any matrix A and any T. So even though this is a good theoretical definition, this is not the way that people usually compute the matrix exponential. So we'll see how to compute it very soon. First, here are some properties of the matrix exponential, which allow us to write the same formula to solve a system of linear equations as the one that we used to solve just one linear equation. So first, the exponential of the zero matrix is the identity matrix. So 0 here, when I write e to the 0, is the n by n square matrix that consists only of zeros. The second property is that the derivative of e to the at is a times e to the at, and it's also equal to e to the at times a. So here, a and e to the at are both matrices, and we know that in general the product of two matrices does not commute, but in this case it does. So a times e to the at is equal to e to the at times a. It's equal to the derivative with respect to t of e to the at. So this is a very natural looking formula. This is what would happen if we had the exponential of a real number. So the derivative of e to the at would be a e to the at. But for matrices, maybe this requires proof, and I'll present it on the next page. And finally, e to the a times t plus s is equal to e to the at times e to the as, and it's equal to e to the as times e to the at. So e to the at and e to the as commute for any two real numbers t and s, actually even for any two complex numbers t and s. And their product is e to the a times t plus s. So these properties are enough to prove the formula for solving systems of linear equations with constant coefficients. So this formula that I presented before, and which involves the matrix exponential. However, the reason why we cannot use this formula, we cannot extend the formula to the case when the coefficients are not constant, is that in general, it is not true that e to the a plus b is equal to e to the a times e to the b. So this is true for real or for complex numbers, but it's not true in general for matrices. So if you have two matrices of the same size, A and B, two square matrices, then e to the A plus B may or may not be equal to e to the A times e to the B. And e to the A times e to the B in general is not equal to e to the B times e to the A. So in general, this is only true if the matrices A and B commute. So AB is equal to BA. In the formula number 3 above, the two matrices are AT and AS. And these two matrices do commute. So the formula is true in that case. I'm not going to present a proof. Again, it's not very hard to prove it, but maybe it's not necessary to do it in this course. So let's prove at least one formula that the derivative of the exponential of AT is A e to the AT. And in the same manner, one can prove that it's equal to e to the AT times A. This proof depends on a theorem which we are not going to present, namely says that the derivative of the sum of a power series is equal to the sum of the derivatives of the terms. So the derivative of the sum is equal to the sum of the derivatives of the terms. And again, the proof is not very different from the one that's true for real numbers, but we're not going to present it here. So anyway, if we want to take the derivative of e to the AT, well, we use the definition. So e to the AT is equal to the sum for n going from 0 to infinity of t to the n over n factorial times a to the n. So then the derivative of this sum is equal to the sum of the derivatives of the terms. So it's equal to the sum of the derivative of t to the n over n factorial times a to the n. But the derivative of t to the n over n factorial is t to the n minus 1 over n minus 1 factorial. And a to the n is constant, so it's not affected by the derivative. So the derivative of t to the n is n times t to the n minus 1. And the n cancels the n in n factorial, and we're left with n minus 1 factorial. Because n factorial is the product of all the positive integers from 1 to n, and then we cancel n, and we're left with the product of all the positive integers from 1 to n minus 1. Okay, so then we have the sum of t to the n minus 1 over n minus 1 factorial times a to the n. And this does not apply to the first term in this infinite sum, which is the identity. So when we set n is equal to 0, we have 2 to the 0 over 0 factorial times a to the 0. This is the identity. So the identity is a constant matrix. And then when you take its derivative with respect to t, we get 0. So then on the next row, I only start the sum from n equal 1 to infinity because the derivative of the first term is 0. Okay, so then all these terms have at least one power of a, so because we start from n equal 1, not from n equal 0, so this means we can factor a. And we can actually factor it from this infinite sum. So then it's equal to a times sum from n going from 1 to infinity of t to the n minus 1 over n minus 1 factorial times a to the n minus 1. Because we factored a. So then instead of a to the n, we have a to the n minus 1. Well, now everything here in this sum is in terms of n minus 1. So let's call n minus 1 our new summation index. So instead of using n minus 1, we replace n minus 1 by n. So then we have sum of t to the n over n factorial times a to the n. And if n goes from 1 to infinity, then n minus 1 goes from 0 to infinity, because n minus 1 is 1 lower than n. Okay, so this is equal to a times, and this sum here is exactly the definition of the matrix exponential. So this is a times e to the at, which is what we wanted to prove. So here is another computation done without the summation notation, just to check that the first computation is not wrong. So, so the matrix exponential is identity plus ta plus t squared over 2a squared plus t cubed over 3 factorial a cubed plus etc. So this is what the summation notation means. And then when I take the derivative of the sum is the sum of the derivatives. So the derivative of the first term, which is the identity, is 0 because the identity is a constant matrix. The derivative of ta is a because the derivative of t is 1 and a is a constant matrix. The derivative of t squared over 2a squared is ta squared because again, the derivative of t squared over 2 is t, and a squared is a constant matrix. So we see that we get a plus ta squared plus t squared over 2a cubed plus t cubed over 3 factorial a to the 4th, etc. And after we factor a from all the terms, then we get a times the identity plus ta plus t squared over 2a squared plus etc. So a times every power is now lowered by 1. And what is here in this parenthesis is, again, the matrix exponential. So this is a times e to the at. So this is the same thing, but without using the summation notation. So how does one compute the matrix exponential? There is a very straightforward method to compute it for diagonalizable matrices. But in order to use it, we need to bring the matrix to its diagonal form. So what is a diagonal matrix first, and then what is a diagonalizable matrix? A square matrix is called diagonal if all its entries except on the main diagonal are 0. And on the main diagonal, they can be 0 or non-zero. So for example, this matrix D with entries 3, 0, 0, 0, 0, 0, 0, 0, 2 is a diagonal matrix because all the entries outside the main diagonal are 0, and on the main diagonal, it has the entries 3, 0, and 2. So the main diagonal is the one that starts from the upper left corner and ends in the lower right corner. So this is a diagonal matrix. And instead of a diagonal matrix, more generally, a matrix is called diagonalizable if there exists a change of basis matrix C, and there exists a diagonal matrix D, which is called the diagonal form of A, such that A is equal to C, D, C inverse. In general, the matrices D and C are not unique. So diagonalizable matrix can be brought to its diagonal form in more than one way. And I want to emphasize at this point that all the matrices we have talked about up to here are square matrices. So A, C, D, C inverse, and the matrix exponential of A are all square matrices. Neither of these notions, so neither diagonalizability nor the notion of a diagonal matrix, nor the notion of matrix exponential makes any sense for non-square matrices. So a very quick review. What is the inverse of a matrix? So what is C inverse, which is denoted by C to the minus 1? A square matrix C is called invertible if there exists another square matrix of the same size, C inverse, which is also called the inverse of C, such that C times C inverse is equal to C inverse times C is equal to the identity matrix. And a practical criterion for invertibility is that a matrix is invertible if and only if its determinant is non-zero. So a matrix with non-zero determinant is invertible. A matrix with zero determinant is not invertible. Let's look at this for 2 by 2 square matrices. So square matrices of dimension 2. Let's consider a square matrix capital A with entries A, B, C, D. Then the determinant of A is AD minus BC. And if the determinant is non-zero, then the inverse, A inverse, is 1 over the determinant of A times the matrix D minus B minus CA. So multiplying a number times a matrix means we multiply each entry of the matrix by that number. So this is the matrix with entries D over the determinant of A, minus B over the determinant of A, minus C over the determinant of A, and A over the determinant of A. And it would be good to also look at 3 by 3 matrices. I don't think I'll ask about them on the final exam, but it's still good to know. So why is it important that a matrix is diagonalizable? So if a matrix capital A is diagonalizable, so A is equal to C, D, C inverse, or for some invertible matrix C and diagonal matrix D, then we can use this to compute the powers of A in a pretty straightforward way. So A to the n is equal to CDC inverse times CDC inverse and CDC inverse, etc., n times. So A to the n is A multiplied with itself n times. So this is CDC inverse multiplied with itself n times. But since multiplication is associative, we can cancel each C inverse by the C that follows it. So C inverse is canceled by C, C inverse is canceled by C, all except for the first C and the last C inverse. These don't cancel because in general multiplication is not commutative. So multiplication of matrices is not commutative. So we get C times D to the n times C inverse. and we cannot swap C and D to the n, so this C does not cancel this C inverse. But in any case, so we get that A to the n is equal to C times D to the n times C inverse. And then the powers of a diagonal matrix are pretty straightforward to compute. D to the n is the matrix that has the same entries as D on the main diagonal, but raised to the power n, and 0 outside the main diagonal. So it's, again, a diagonal matrix. And the same is true for the exponential. So the matrix exponential e to the at is sum of t to the n over n factorial times a to the n. And we replace a to the n by c d to the n c inverse. And we factor a c to the left and the c inverse to the right. And then what is left inside the sum is sum of t to the n over n factorial times d to the n. And this is the matrix exponential of dt. So e to the at is c times e to the dt times c inverse. And again, we cannot commute c and e to the dt, so this is the final answer. And the reason why this is helpful is that computing the exponential of a diagonal matrix is pretty straightforward. Again, one just takes the exponential of each entry on the diagonal, and all the entries outside the main diagonal remain 0. So the exponential of a diagonal matrix is again a diagonal matrix, but with each entry on the main diagonal replaced by its exponential. So how does one see this? If D is a diagonal matrix that has the numbers lambda 1, lambda 2, up to lambda m, so it's an m by m matrix, which has these m numbers on the main diagonal and 0 everywhere else, then by taking its product with itself n times, you can see that d to the n is again a diagonal matrix that has lambda 1 to the n, lambda 2 to the n, up to lambda m to the n on the main diagonal, and 0 everywhere else. So now we use this fact about d to the n in the definition of the matrix exponential e to the dt. So e to the dt is sum of t to the n over n factorial times d to the n. But each matrix d to the n will just have lambda 1 to the n, lambda 2 to the n, up to lambda m to the n on the main diagonal and 0 everywhere else. And then when one takes the infinite sum with these coefficients t to the n over n factorial, then one just gets the sum of t to the n over n factorial times these numbers raised to the power n on the main diagonal, and 0 everywhere else, because all the powers of d are 0 everywhere off the main diagonal. So on the main diagonal, on the other hand, this is the definition of the exponential of a real number. So it's the exponential of t lambda 1 for the first entry, and then it's the exponential of t lambda 2 for the second entry, etc. So we get these exponentials on the main diagonal, e to the t lambda 1, e to the t lambda 2, up to e to the t lambda m, and again 0 everywhere else. So it's very straightforward to compute the exponential of a diagonal matrix. So here's an example. If D is the diagonal matrix I mentioned before, so the matrix with entries 3, 0, and 2 on the main diagonal and 0 everywhere else, then the exponential of dt is the diagonal matrix with entries e to the 3t, e to the 0 times t, and e to the 2t on the main diagonal. And knowing that e to the 0 times t is e to the 0, which is 1, so we get the matrix with entries e to the 3t, 1, and e to the 2t on the main diagonal, and 0 everywhere else. So for particular values of t, for example, e to the d is the matrix with entries e cubed 0, 0, 0, 1, 0, 0, 0, e squared. So this means it has the entries e cubed, 1, and e squared on the main diagonal, and 0 everywhere else. And e to the minus d is the matrix with entries e to the minus 3, 1, and e to the minus 2 on the main diagonal, and 0 everywhere else. Or for example, e to the 2d is the matrix with entries e to the 6, 1, and e to the 4 on the main diagonal, and 0 everywhere else. So all three of them are diagonal matrices. Now let's do the computation for a diagonalizable matrix, which is not diagonal. So let's consider the 2 by 2 matrix, capital A, with entries 2, 5, 5, and 2. Then this matrix is diagonalizable, and in the next course, we'll see the procedure to find the matrices C and D. For now, let's just list them. So A is equal to C, D, C inverse, where C is the matrix with entries 1, 1, 1, minus 1. And D is the matrix with entries 7, 0, 0, minus 3. So it is a diagonal matrix with 7 and minus 3 on the main diagonal and 0 off the diagonal. And C inverse is the matrix, well, we use the formula for inverting the matrix C, and we get that it is the matrix with entries 1/2, 1/2, 1/2, and minus 1/2. Right? So then the exponential of AT is C times the exponential of DT times C inverse. So this is, the matrix C is still the same, so 1, 1, 1, minus 1. The exponential of dt is the diagonal matrix with entries e to the 7t and e to the minus 3t on the diagonal and 0 off the diagonal. And C inverse is the matrix, again, we have it from the previous computation. So it's 1/2, 1/2, 1/2, and minus 1/2. Okay, so all three matrices, or all the matrices in this computation are square 2 by 2 matrices. Okay, so then e to the AT is the product of these three 2 by 2 matrices. And we do the products step by step. For example, we first take the product of the first two matrices, and then we multiply it with the third matrix as well. So we get, so the product of the first two matrices is the matrix with components e to the 7t, e to the minus 3t, e to the 7t, and minus e to the minus 3t. And then when we take the product with the third matrix as well, we get 1/2 times e to the 7t plus e to the minus 3t. And then the second entry is 1/2 times e to the 7t minus e to the minus 3t. And this is equal to the third entry. So the third entry is also 1/2 times e to the 7t minus e to the minus 3t. And the fourth entry is the same as the first. So it's 1/2 e to the 7t plus 1/2 e to the minus 3t. And this is not completely a coincidence. So there are some symmetries. In particular, the matrix A is symmetric, which leads to the exponential of the matrix A also being symmetric. So now let's use this computation to solve an initial value problem. Let's consider the initial value problem. So let's consider the system of two equations with two unknown functions, x of t and y of t, such that x prime is equal to 2x plus 5y, and y prime is equal to 5x plus 2y. And with the initial conditions, x of 2 is equal to 1, and y of 2 is equal to 3. Okay, so then the coefficient matrix is this matrix 2, 5, 5, 2. And so let's form a common vector from the unknown functions. So let's form the vector capital Y of t with components x of t and y of t. Then the problem can be written as y prime is equal to a times y. So where y is the scalar vector with two components, and a is the square matrix 2, 5, 5, 2. And with the initial conditions, so y, capital Y of time 2 is the common vector with components x of 2 and y of 2. So it's the vector with components 1 and 3. Okay. So then, first, this is a homogeneous equation. There is no source term. And then the solution is given just by a matrix exponential. So y of t is equal to e to the a times t minus 2 times y of 2. So here, e to the a times t minus 2 is the matrix exponential of a to the times t minus 2. And y of 2 is the column vector consisting of the initial conditions. Okay? So since we already computed the matrix exponential e to the at on the previous page, then we know what e to the a times t minus 2 is. We just replace t by t minus 2 in the formula from the previous page. So y of t is the matrix with the following components. So actually, first let's say what the matrix exponential is. So e to the a times t minus 2 is 1/2 e to the 7 times t minus 2 plus 1/2 e to the minus 3 times t minus 2. The second component is 1/2 times e to the 7 times t minus 2 minus 1/2 e to the minus 3 times t minus 2. The third component is the same as the second component, and the fourth component is the same as the first component. So this is because the coefficients of the original system 2, 5, 5, 2 are very symmetric. So we get a matrix exponential that also looks very symmetric. But in general, this is not true. So in general, all four entries may be distinct functions, maybe different functions. Okay. So this is the matrix exponential. e to the a times t minus 2. And then this is times the column vector y of 2, which is the column vector with entries 1 and 3. Okay, so we carry out the multiplication, then we get again a column vector, which is as it should be because y of t is a column vector. So it's the column vector with entries 2 e to the 7 times t minus 2 minus e to the minus 3 times t minus 2. And the second entry is 2 e to the 7 times t minus 2 plus e to the minus 3 times t minus 2. So this looks very symmetric, surprisingly symmetric. In general, it should not look like this. So the two entries will be a little bit more different from each other. So we computed this vector capital Y of t, but the two components of capital Y of t are x of t and y of t, the two unknown functions we wanted to compute. So this means that x of t is the first entry and y of t is the second entry. So x of t is 2 e to the 7 times t minus 2 minus e to the minus 3 times t minus 2. And the second entry is y of t, so lowercase y of t, which is 2 e to the 7 times t minus 2 plus e to the minus 3 times t minus 2. You can check by plugging these into the original system that they solve the system and they also satisfy the initial conditions. So this is how we solve a system by using the matrix exponential. In the next course, we'll look at how to diagonalize a matrix and how to determine whether a matrix is diagonalizable or not. We'll give more examples, including examples where the system is inhomogeneous. And we'll also say some words about the case when the system matrix is not diagonalizable. Or maybe we'll do that on Friday. Or maybe we'll do that next week. Thanks for your attention and have a great day.